Today, I'm calling Polynomial Day. Why? Because we're going to talk all about polynomials. You might say, well, didn't we do that at the beginning of the semester? And yes, we did, but we're going to go into much more depth today. Why? Because our main theme for the rest of the next 3 or 4 weeks or so is going to be using polynomials to interpolate other functions, to approximate other functions. So we want to know as many things as we can know about polynomials as possible. In fact, that's what I'm going to try to get across today, is learning as much about polynomials as we can, both through some theory and through some computation, both by hand with calculator help and Mathematica. So what is a general nth degree polynomial? It's a function whose highest power of x is nth power. Call it P of x for polynomial. In general, written a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power, right? You see the pattern here, plus a sub n minus 2 times x to the n minus 2 power, etc. You know, for most examples, n is 1 or 2 or 3 or 4 or maybe 5 if you're unlucky. But in theory here, n could be 1,000,000, it could be 1,000,000,000, it could be a Google. It could be unimaginably large polynomial. We just don't deal with such situations in the typical kinds of problems. But we go down to a2x squared plus a1x plus a0. These a's are called the coefficients of the polynomial. The a's are the coefficients. I'm using I for a general subscript here. I goes from 0 up to n. They are typically, for most examples, integers, right? 0 plus or minus 1 plus or minus 2 plus or minus 3 for most examples, including 0. So if 0 is a coefficient, you would not see that term, right? If you, for example, if you were thinking of the polynomial x cubed plus x plus 1, I didn't say x squared in there. The coefficient of x squared would be 0, so you would not bother writing it. So these a's could be 0. You are assuming in saying it's nth degree that an is non-zero. If you're saying it's nth degree, then an would not be 0. Actually, in the general theory, if you allowed for even higher coefficients with bigger subscripts, yet the polynomial is still nth degree, you would just say all those other coefficients are all zeros because you have the highest power being nth power there. This has got a name. It's called the leading coefficient. Leading coefficient. And again, it's non-zero. A0 has got a special name as well. It's called the constant term or constant coefficient. I'll call it constant term. It's more what I'm used to. What if n is 0? Would the degree be 0? If it was just a constant? Yeah. You can have constant polynomials. P of x equals a0 is a constant polynomial. It's called a constant polynomial. And you would say it's got degree 0, except for some technicalities that I'm not going to get into, if a0 actually is 0, and it's the 0 polynomial. Technically speaking, we say the 0 polynomial has no degree. It's an undefined degree. I don't want to get into reasons why for technicality. But otherwise, if a0 is non-zero, you'd call it a constant polynomial with a degree of 0. But the 0 polynomial is a polynomial. A0 could be 0. And I guess in that case, you'd be violating this condition right here. Okay? That's just sort of a special case. So there's your general nth degree polynomial. What do we want to do with polynomials? What have you done in the past? We want to find the roots. This is one of the most basic things you want to do. And how do you do that? Typically with factoring. With linear polynomials, it's easy. They're already factored, right? They're already set equal to 0. You can easily solve for x. With quadratics, you can try factoring by trial and error. but sometimes it's difficult. And so you rely on the quadratic formula, maybe because some of the roots are irrational numbers, some of the roots are complex numbers, that kind of thing. Once you get to cubics, already when n is just 3, it gets really hard. I'll remind you from the first day of class that technically speaking, solving a cubic is possible. Solve a general cubic. Okay, I'll go ahead and write a3 times x cubed plus a2 times x squared plus a1 times x plus a0 equals 0. Solve for x, and Mathematica spits back some answers. Yikes. 3 answers, technically speaking. There's one of them. Here's another one. And here's another one. These all could be real numbers in the end. You could have 3 real roots. You could have 1 repeated real root. Well, and 1 regular real root, non-repeated. That's still 3 real roots. The graph could look like this, for example, and just touch the axis over there. That would be a double root over there and a root of multiplicity 1 right here. Still no complex roots. Or you could have just 1 real root and 2 complex roots. Okay. If we've got particular numbers in here for the a's, and we try using solve to solve this in general, maybe 2x cubed plus 5x squared minus 7x plus 4 equals 0, solve for x. Mathematica by default with solve actually gives numerical approximations. But if you add in the option cubics arrow true, it will give you exact versions. Often you see the imaginary unit I in there. That doesn't actually mean these are all complex numbers, or even this one's a complex number. It's possible the i's could cancel out in a certain degree. Mathematica is writing things in funny ways. We don't really worry about it, okay? Just realize it's possible to do, and we can certainly approximate those things. All right? We know the graph, you should remember from calculus, of an nth degree polynomial depends on whether n is even or odd, and also depends on whether the leading coefficient is positive or negative as far as the n behavior goes. So like, for example, if n is odd and an is positive, what's the n behavior? It's like this. I'll just draw arrows. I'm not going to draw a full graph. In other words, the function goes off to plus infinity as x goes to plus infinity, and minus infinity as x goes to minus infinity, with some possible wiggles in between. If n is odd and an is negative, the n behavior flips like this, with some wiggles in between. If n is even and an, the leading coefficient, is positive, then these arrows indicate the n behavior going up to positive infinity as x goes to positive infinity or minus infinity. And if n is even and an is negative, it's like you're flipping it across the horizontal axis and you're going down forever and ever. Realize that in these last 2 pictures, I'm not ruling out the possibility of real roots, right? You could cross the axis here. Coming back to the general formula for a polynomial, I said a few minutes ago that the a's are typically integers. But in this class, and in, for example, abstract algebra, you want to allow for other kinds of coefficients. They could be rational numbers, fractions, 5/3, 17/15, negative 34 30/3, right? They could be rational numbers that are fractions and not integers. We even want to allow for irrational coefficients, square root of 2, pi, and even complex number coefficients. Yikes. Some of those a's could involve the imaginary unit. Now, we're not going to typically consider such examples, but some of the theory that I'm going to mention today is still relevant for those examples. I will quickly remind you that when the a's are integers, roots of such equations are called Real roots are called algebraic numbers. And there are transcendental numbers like pi and e that do not solve such polynomial equations where the a's are integers, just to remind you of that. Okay, so that's the basics of what we know so far. What else can we say about polynomial functions? Well, there's something called the division algorithm that is a useful thing to know. It's called an algorithm, but it's really a theorem. Those who've had abstract algebra know about the division algorithm for integers. And if you had it last year, you even know about the division algorithm for polynomials, which I'm about to state here. Suppose f of x and g of x are polynomials. I'm not going to state their degrees, but they would have some kind of degree here. With what kind of coefficients? Let's allow complex coefficients. Now, when I say complex coefficients, realize that all those complex numbers that are coefficients could also be real numbers, because real numbers are complex numbers. Any real number like 5 could be thought of as a complex number, 5 plus 0i. Real numbers are complex numbers. The real number field is a subset or subfield of the complex number field. Even an irrational number like square root of 2 could be thought of as a complex number. The part in front of the I, the imaginary unit whose square is -1, would be 0. So when I say that, this includes all numbers. For us, integers, rational numbers, irrational numbers, general real numbers, which are either rational or irrational. I am putting all in quotes because there are other number systems. There's something called quaternions and octinions, and what are those? I'm not going to get into that, but we're restricting ourselves to ordinary real numbers and complex numbers. F of g and g are polynomials with complex coefficients, and say g of x is not the 0 polynomial. So I'm not saying g at a specific value of x is not equal to 0. I'm saying g of x is not the 0 polynomial. When I write that, not the 0 polynomial, it's not identically equal to 0. Then I can divide f of x by g of x and get a quotient and a remainder, just like you can with numbers. Then there exists polynomials. Already use a big backwards E for there exists. Polynomials. Call them Q of x and R of x. In fact, they are unique polynomials that satisfy certain conditions. Backwards E with an exclamation point does not mean backwards E factorial. It means there exists unique. If you want to make a little note to yourself, there exists unique polynomials Q of x and R of x such that f of x equals g of x times q of x plus r of x, and either r of x is the 0 polynomial or the degree of r of x. Deg rx means degree of r of x is less than the degree of what we're dividing by, which is the g of x. I'm imagining dividing f of x by g of x here. And in fact, this equation is equivalent if I divide both sides by g of x to the equation f of x divided by g of x equals q of x plus r of x over g of x. I just divided both sides by the non-zero polynomial g of x here. These two equations are equivalent to each other. Let's do an example to illustrate this. Let's do one by hand. Oh, let's say we want to effectively figure out how we could simplify x cubed plus 1 over x squared plus 1. Want to divide x cubed plus 1, that's my f of x, by the polynomial g of x equals x squared plus 1. How do you do it? How do you figure out the q of x and the r of x? You can do polynomial long division. Write it like that. Ask yourself, what do I need to multiply x squared by, the highest power here, to get the highest power here, which is x cubed? Well, you need to multiply it by x. X squared times x equals x cubed. Then take what you've written up there, that x, and multiply times each term and put the answers down here. X times x squared is x cubed. X times 1 is x. Then subtract. After subtraction, you will get minus x plus 1. We can actually stop right now. Once we don't have to continue, sometimes you have to continue here. But in this example, we can stop right here because we're left with the polynomial now, right there, that has a degree smaller than what we're dividing by. That means this is the remainder. When I divide x cubed over x cubed plus 1 by x squared plus 1. So this is the remainder. This is the r of x. And the thing up here is the quotient. So what we're saying by this is x cubed plus 1 over x squared plus 1, if I want to think of the division algorithm this way, is the quotient x plus the remainder negative x plus 1 over the original g of x, the thing we're dividing by. I forget what that's called, a dividend or something like that. X squared plus 1. Equivalently, we could also write x cubed plus 1 equals x squared plus 1 times x plus, in parentheses, say negative x plus 1, though I could get rid of those parentheses. The x is the q of x again, that's the quotient. The negative x minus a plus 1 is the r of x, that's the remainder. Probably should check it. Check it by expanding this side or by adding these fractions up here by getting a common denominator, but it's equivalent to expanding this. Expand that out. X squared plus 1 times x will give you x cubed plus x. And then we have a minus x plus 1. Yeah, the x's cancel, leaving you with x cubed plus 1. It checks. Again, when you're doing long division, if I had gotten something of degree 2 or higher here, I would have had to continue. I can stop in my long division once the remainder, once the thing that's there has a degree less than what's there. And sometimes you get a constant here. And that would mean the remainder is a constant. And sometimes that constant is 0. And when the remainder is 0, that's especially nice, actually, because that means g of x is a factor of f of x. If r of x is 0, that goes away, and you could say f of x is g of x times q of x, meaning g of x is a factor of f of x. Okay, that's pretty nice. Let me do another example. And in this example, I'm going to do it 2 ways. I'm going to use long division, but I'm also going to use something called synthetic division. Let's say we're trying to figure out x cubed plus 1. Let's make it let's see, what should we do here? Divided by x plus 1. If I do this with long division, what happens? Again, I look at the highest power here, the x, ask what should I multiply x by to get x cubed? The answer is x squared. Put that answer here. Then take that thing and multiply times each term. X squared times x is x cubed. X squared times 1 is x squared. Subtract. I get a negative x squared plus 1, whose degree is not smaller than x plus 1. So I have to keep going. Ask what should I multiply x by to get negative x squared? I have to multiply it by negative x. Then take that negative x and multiply it times each of these. Write the answer down here. Negative x times x is negative x squared. Negative x times 1 is negative x. Careful, you're subtracting. The negative x squareds canceled, but with these two things, the negative sign comes through. I end up with positive x plus 1. And guess what? X plus 1 goes into x plus 1 one time. So I get a plus 1 here, and then when I multiply plus 1 times x plus 1, I get x plus 1, and when I subtract, I get a remainder of 0. X squared, x plus 1 is a factor of x cubed plus 1. There's your remainder, there's your r of x. It is the 0 polynomial. And here's your quotient. In other words, you could write x cubed plus 1 over x plus 1 as the quotient, x squared minus x plus 1, plus the remainder 0 over what you were dividing by. But because that's a 0 there, I don't have to write it. I can just write that. Equivalently, I could write the original polynomial, x cubed plus 1 is the quotient, x squared minus x plus 1 times what I was dividing by, x plus 1 plus 0. But I don't have to write plus 0. How is this useful? It's useful in a number of ways. Coming back to the first example, one way this is useful, this equality here is useful, is helping you graph this function, for example. And in particular, to see that it's got something called a slant asymptote. Think about it with me here. If your task was to graph the rational function x cubed plus 1 over x squared plus 1, because it equals this, you could say, as x goes to plus or minus infinity, this part right there, that fraction, goes to 0, doesn't it? Because the degree of the bottom is bigger than the degree of the top. Excuse me. So in the long run, this function here, this rational function, approaches this function x. This equality means that x cubed plus 1 over x squared plus 1 is approximately equal to just x when the absolute value of x is large. How large is large? I'm not saying. Yeah. We could go ahead and make it. Let's go ahead and make a graph to see these things. X cubed plus 1 over x squared plus 1. And let's also plot the function x. Y equals x. In the same window, say negative 10 to 10. There you have it. The blue graph is the rational function. The yellowish graph is y equals x. Go a little closer to the origin here. Right. There we go. You can see how that is a slant asymptote. It actually looks like it's more parallel here, but it would have to be getting closer and closer to it. Because again, this part right here goes to 0 as x goes to plus or minus infinity. Because the degree of the bottom is bigger than the degree of the top. Likewise, in the second example, well, this fact would help you find the roots of x cubed plus 1. That's one application of this. One root would be -1. Another root would be found by setting this equal to 0 and solving for x with the quadratic formula, though I will tell you you'll get complex answers. Let's go ahead and find them. I do want to come back to the using synthetic division here in a minute, but if I set this equal to 0 and solve for x, one root is x is -1. Other roots occur where x squared minus x plus 1 is 0, and with the quadratic formula, that'll give you 1 plus or minus square root of 1 minus 4 over 2. I didn't make a mistake there. 1/2 plus or minus square root of -3 over 2. Square root of -3 is the same as I times the square root of +3. So you get these roots. Interesting thing here, -1 and these two complex numbers have a nice visualization you can do with them. They're all on the unit circle in what's called the complex plane. What is the complex plane? Well, the complex plane is just an ordinary plane with axes labeled real and imaginary, and points plotted, complex numbers plotted as if they were points. 1/2 plus I square root of 3 over 2 corresponds to the point whose coordinates are 1/2 square root of 3 over 2. The natural thing to do. Where is that? Well, it'd be right about here. And 1/2 minus I times square root of 3 over 2 would correspond to the reflection of that point across the real axis. And -1 is over here. These are all on the unit circle in the complex plane, a circle centered at the origin with a radius of 1. And they're all really cube roots of -1 because they solve the equation x cubed plus 1 equals 0, meaning they solve the equation x cubed equals -1. There are 3 cube roots of -1 that are all in the unit circle. And in fact, they are at 120-degree angles from each other. Kind of cool. Think about the trigonometry there. Those 120 degrees there, 120 degrees there, 120 degrees there. Kind of a cool thing. You also could think about using this to this equality here to graph this function. In fact, what the equality here would say is the graph of this rational function is actually a parabola because it's a quadratic. Wait a minute. Wouldn't we be dividing by 0 if x is -1? Yeah, it's a parabola with 1 point missing. A parabola with 1 point missing. Let's go ahead and graph it. I'll just graph the one function this time. Yeah, it looks like a parabola. Where's the missing point? It's at x equals -1. Mathematica, you can't see the point is missing. But you know it's missing because technically the original function is undefined at x equals -1. But the limit exists as x approaches -1. This is a calculus kind of problem. The limit of this thing as x approaches -1 does exist because technically speaking, the limit is unaffected by the fact that the function is undefined at -1. Because these two functions are equal when x is not -1, their limits are the same. And you can evaluate this limit by the fact that this function here is continuous at -1. You can just plug in -1 and get 1 plus 1 plus 1, 3. The limit is 3. All right, what about synthetic division? Maybe you've seen synthetic division, maybe not. Did we do it the first day of class in here? We might have. Synthetic division allows you to take x cubed plus 1 and divide by x plus 1 by a method somewhat similar to long division, but with some twists. Instead of putting an x plus 1 to the left here, you put the root itself, -1. And with the polynomial you are dividing into, the top of the fraction here, you put its coefficients and no x's underneath the bar here, including coefficients that are 0. X cubed has a leading coefficient of 1, put a 1 there. There's no x squared or x terms, put zeros. You've got to put the zeros. And then the constant term is 1, put a 1. Then instead of multiplying and subtracting, you multiply and add. It's kind of weird, but this is the way it works. You first bring this down 1 down here, effectively adding 1 plus 0 to get 1. Then you multiply this number, -1 times that number, 1, to get -1, and put the answer here. Then you add, don't subtract. 0 plus -1 is -1. Multiply, -1 times -1 is +1. Add, 0 plus 1 is 1. Multiply, -1 times 1 is -1. Add, 1 plus -1 is 0. That number that you get right there is the remainder. When dividing x cubed plus 1 by x plus 1, like we already did, we already saw we got a remainder of 0 before. And the other coefficients down here, the 1, the -1, and the 1, are the coefficients of the quotient. 1, -1, 1. Compare that with this. Coefficients are 1, -1, 1. That's the coefficients of the q of x. That's a lot faster. And again, the fact that we got a remainder of 0 means -1 is the root of the polynomial, x cubed plus 1. It is a cube root of -1. But it gets even better with synthetic division. You can use synthetic division to evaluate polynomials at any number. For example, so my polynomial in this example here, the thing I'm dividing into is x cubed plus 1. Let's take that to be the p of x. X cubed plus 1. What if I want to evaluate this polynomial at x equals -2? Well, of course, you could do the usual thing. You could plug in -2. It'll give you -8 plus 1, -7 in the end. But you also can evaluate this polynomial at this number with synthetic division. In fact, we already did that when we plugged in -1 and got 0 here. P of -1 is 0. But you can do it for numbers like -2 that are actually not roots. Put a -2 here, keep the same coefficients of x cubed plus 1, 1, 0, 0, 1. Do the same process. Bring down the 1. In effect, 1 plus 0 is 1. Multiply, -2 times 1 is -2. Add, 0 plus -2 is -2. Multiply, -2 times itself is +4. Add, multiply, add, lo and behold, we get -7. Just like we got there. There's a match. That number is P of -2. The numbers we got down here, 1, -2, and 4, are different than these numbers. Can we still interpret what they mean? Yep. You can still say, and this is a theorem in the book, the basis of something called Horner's method, which is what we effectively just did, Horner's method. is what we did to evaluate p of -2. We used synthetic division to evaluate the function. Horner's method is going to say p of x, which is x cubed plus 1, can be written as, well, we were evaluating at -2 here. A factor x plus 2 times a quadratic in this case, whose coefficients are what you see here, 1, -2, and 4, x squared minus 2x plus 4, and then add the remainder, which is -7. Adding -7 is the same as subtracting 7. So that -7 goes over there, and these coefficients go over here. I've effectively used something called Horner's method to evaluate the polynomial. I use synthetic division to evaluate the polynomial, even at a number that's not a root. This is actually a useful thing. We should probably check it. Check it by expanding. So multiply this out. Got a binomial times a trinomial. I'm going to take the x times every term first. Get x times x squared is x cubed. X times -2x is minus 2x squared. X times 4 is plus 4x. Now go to the 2 and multiply it times each term. So I get plus 2x squared minus 4x plus 8. Don't forget the -7. Simplify by combining like terms and canceling if you can. Yeah, we can cancel. And 8 minus 7 is 1. This does indeed simplify to x cubed plus 1. It did work. Let's try to come up with another example to illustrate this. Talk about some other things related to this other example, and then we'll apply Horner's method again to illustrate it. And then we're also going to talk about applying this to Newton's method. We're not done with Newton's method. Okay, we've talked about Newton's method plenty, but we're not quite done with it, because Horner's method is a useful thing to apply with Newton's method, especially if all you have handy is a calculator. What kind of example do I want to come up with here? Well, let's go to Mathematica and expand a polynomial that's in factored form so that I can see the roots easily. Oh, and let's make one of the roots a non-integer. Maybe, well, let's make it 4/3. If 3x minus 4 is a factor, then 4/3 is going to be one root of this polynomial. Let's make it 4th degree. Maybe 1 will be another root. Let's make it a little further away from 4/3. How about 2? -1 will be another root, and -2 will be another one. So the roots of this, because we know the factored form ahead of time, are going to be positive 4/3, positive 2, -1, and -2. There it is. Let's go ahead and just write it down. That's going to be my p of x. 3x to the 4th minus x cubed minus 16x squared plus 4x plus 16. Did I write it down right? Looks good. Before we apply Horner's method, and our ultimate goal here with Horner's method is to understand why it works. Why does using synthetic division work to evaluate values of a polynomial? But before we do that, let's explore some other things here that you may or may not have learned in the past. Say I put this polynomial on a test, and my directions are find its roots. You wouldn't know what the factored form is right away, right? You wouldn't know how to factor it. In general, this could be a pretty hard problem. Now, you could use your calculator to graph it and guess the roots and try to use either synthetic division or long division to help you factor it. But in the general case, that's actually not guaranteed to work because the roots might not be nice numbers. They could be irrational numbers. Your guess of a root, for example, at 2 could be wrong. Maybe the true root is just barely bigger than 2. Some irrational number just barely bigger than 2. So what we do in the old days when we didn't even have calculators, in the old days, we had to start with a theorem, maybe even a couple theorems, one of which is called the rational root theorem, and another theorem called Descartes' rule of signs. And I would like to spend time informing you about those theorems. You can look them up on Wikipedia, for example. So what does the rational root theorem say? It's a constraint on the possible rational solutions of a polynomial equation when the coefficients are integers. Z here means integers. Z is shorthand for the German word Zahlen, which effectively means integer. What does the theorem say? It says each rational number solution, P over Q, where P and Q are integers, and written in lowest terms so that P and Q, in fact, are relatively prime, satisfies these conditions. The numerator must be a factor of the constant term, A0, and the denominator, Q, must be a factor of the leading coefficient, AN. Careful, this does not guarantee that there will be any rational roots. It's possible all the roots could be irrational numbers. In fact, that's the typical case, that all the roots are irrational numbers. You have to, as a teacher, come up with examples for your students where the roots are rational, like we just did with Mathematica, in fact. Also, some of them could be complex numbers. This just says that if there are any rational roots, P over Q, then these conditions have to be true. So it gives you conditions on the possible rational roots. And what I remember doing in high school back in the 1980s was saying, okay, yeah, again, what are the possibilities for the numerator P? They've got to divide A0, the constant term. The possibilities for P are the divisors of 16, integer divisors, including negative possibilities. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16 are the possibilities for P. The possibilities for the denominator of any rational roots are the factors of 3, plus or minus 1 and plus or minus 3, giving you possibilities for P over Q to be all possible fractions, distinct fractions that you can make from these ratios. Plus or minus 1, plus or minus 2, plus or minus 4. If I just divide all these by plus or minus 1, but also plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, plus or minus 8/3, and plus or minus 16/3. Now, again, we already know the answers are 4/3, 2, -1, and -2. And those are all rational numbers, and they are all in these lists. 4/3 is the positive one of those, +2, -1, and -2 are the actual rational roots in this case. But we, without calculator technology, without graphing calculator technology, had to test these. And if you got lots of possibilities, that's lots of numbers to test. Ultimately, again, the answers are for the roots, where we set this equal to 0 and solve for x, are 4/3, 2, -1, and -2. How did we test? We use synthetic division. And again, I'm going to come back to synthetic division. Let me also talk briefly about Descartes' rule of signs. Am I going to test you on these things? I don't know yet, so don't rule it out. Descartes' rule of signs, what does it say? The rule states that if you got a polynomial and you look at the non-zero terms where the coefficients are real numbers, they could be irrational, but they're real, not complex. The number of positive roots is either equal to the number of sign changes from a plus to a minus sign or from a minus sign to a plus sign between consecutive non-zero coefficients, or is less than that number by an even number. What a weird rule. A root of multiplicity k is counted as k roots. And with negative roots, you do the same kind of thing, except effectively you replace the x's by negative x's to get a new polynomial that you count the sign changes of. So could we apply this here for this example? Look at our polynomial here. Go from highest degree to lowest degree. Look at the coefficients. 3, -1, -16, 4, 16. How many sign changes are there? From positive to negative there's 1. And from negative back to positive there's 2. There are 2 sign changes. So there are either 2 positive real roots or 0 positive real roots, is what Descartes' rule of signs would say. It's either the number of sign changes or it's less than that number by an even number. There can't be 1 positive real root. And there also can't be more than 2. It's either 0 or 2. We know the answer is 2. As far as negative real roots, you look at a different polynomial where you replace each x with negative x, which effectively changes the sign on the odd powers of x and not the even powers. You'd be thinking about this polynomial, 3x to the 4th plus x cubed minus 16x squared minus 4x plus 16. I changed the sign on the odd powers of x, not the even ones. This new polynomial has 1, 2 sign changes as well. And that means the negative real roots of the original polynomial are either 2 or less than 2 by an even number. So again, either 0 or 2 of them, and there are 2 of them. So a couple real quick examples to illustrate the rational root theorem and Descartes' rule of signs. Historically, those are pretty important theorems. They're a little less important nowadays because we have the technology, so why bother? That's sort of the idea now. But I think it's worthwhile for you to know about them as a couple rules related to roots of polynomials. But mostly we want to get back to Horner's algorithm again, Horner's method. Again, you could test these answers with synthetic division. Let's in fact test the 4/3 one. Let's test the fraction one to illustrate that it's working. 4/3. I'm doing synthetic division. I look at those coefficients. None of them are 0 this time. Again, if any terms are missing, that means it's got a 0 coefficient, and that does have to be included. 4 and 16. Bring down that 3. Multiply 4/3 times 3. Hey, is 4. That's nice. We got rid of the fraction. Add. Oh no, is the fraction going to come back? Well, 4/3 times 3 once again is 4. Add -16 plus 4 is -12. Multiply 4/3 times -12 is what? -16? Yep. Add 4 plus -16 is -12. 4/3 times -12 is -16. Add, get 0. Yay! There's our remainder. That is also the value of P of 4/3 is what Horner's method says. And that's confirming 4/3 is a root. That's easier to do by hand. And here's the punchline with Horner's method. This synthetic division is easier to do by hand to confirm P of 4/3 is 0 than to plug 4/3 up there, right? Because you, for example, would have to compute 4/3 to the 4th power. 4/3 to the 4th power, what would that be? 4 to the 4th, 256 over 81 times 3, and then minus 4/3 cubed, minus 16 times 4/3 squared. You got a bunch of fractions. That's more computationally intensive than doing this. Especially if all you have is either just your mind or a basic calculator. And once again, these are the coefficients you get when you divide this polynomial by, careful here, x minus 4/3. This means, if I combine all these things, that 3x to the fourth plus x cubed minus 16x squared minus 4x plus 16 can be factored as x minus 4/3, not 3x minus 4, but x minus 4/3, times this, the polynomial with these coefficients. There's the constant term, there's the x term, there's the x squared, there's the x cubed. It would be 3x cubed plus 3x squared minus 12x minus 12. But don't we typically try to get rid of fractions in a factorization? You might say yes. You don't have to, but we could get rid of it by factoring a 3 out of this one, like this, and then distributing that 3 through the parentheses here. So another way to write your factorization is as 3x minus 4, but then times x cubed plus x squared minus 4x minus 4. If we suspected, going back to knowing what the roots are, 2, -1, and -2 are continue to be roots, they would be roots of this. I could continue the synthetic division downward. For example, I could put a 2 here, do synthetic division here, bring down the 3, multiply, add, multiply, add, multiply, add, and I get a 0 again, meaning 2 is a root of this polynomial, but that also means it's a root of the original polynomial. And then I could continue. I also could use the quadratic formula at this point from the other roots, or factor the quadratic just by looking at it, because they're fairly simple, -1 and -2. Get the idea? You're okay if I don't finish it here? Why does this work? Why does Horner's method work? It's based on going back to the original polynomial. I mean, the book gives a proof of it in the abstract. Well, let's just think about it for this example. Why does this method work? Let me rewrite this polynomial down here. Why can we evaluate this polynomial, for example, at 4/3 by doing synthetic division instead of plugging the number in? It's based on a little trickery. And what's the trickery? Let me first rewrite this polynomial by factoring out a common factor out of the first 2 terms. What's a common factor of the first 2 terms? X cubed is a common factor of the first 2 terms. Factor it out. What a weird thing to do. Well, the weirdness is going to continue. Now factor a common factor out of these 2 terms. Sort of pretending 3x minus 1 is like a constant, even though it's not. Those 2 terms have an x squared in common. Factor it out. Like this. Well, again, you could say, what a weird thing to do. But it's certainly doable. If I haven't made a mistake, it's certainly okay to do. Now factor a common factor out of these 2 terms. X is a common factor. Ugh, lots of parentheses here. 3x minus 1 times x minus 16 in parentheses times x times in parentheses plus 4. I factored out an x. If I've not made a mistake, this is another way to write this polynomial. You could call this the standard form of the polynomial. And you know, what is this? Is it a factored form? Well, not in the usual sense, right? Because usually with a factored form, you're looking for the roots. These factors, so to speak, like the 3x minus 1 and this entire thing in this set of parentheses and this entire set of things in this parentheses, are not factors in the usual sense. This is actually called the nested form. Now, imagine plugging 4/3 into this in the nested form. What would you get? You'd first start here inside, right? 4/3 times 3 is 4, minus 1 is 3. Just like this 3 that is obtained as 3 times 4/3, 4 minus 1. Say that again. Imagine plugging 4/3 in here. You do 3 times 4/3 minus 1. Ultimately, 4 minus 1 is 3. That's the same sequence of calculations we did to get this 3. 3 times 4/3 is 4, minus 1 is 3. Negative 1 plus 4 is the same as 4 minus 1. Then you'd multiply that by 4/3 and subtract 16. Just like we multiply this number by 4/3 and subtract 16 to get negative 12. Then you'd multiply by 4/3 again and then add 4. Multiply negative 12 by 4/3 to get negative 16, then add 4 to get negative 12. Then finally, you'd multiply by 4/3 once more and add 16. Just like we took this negative 12, multiplied by 4/3 to get negative 16, and added 16 to get 0. The nested form is illustrating why Horner's method works for this example. Why you can evaluate the polynomial with synthetic division. It's not a proof because it's not a general argument, but that is the gist of the general argument using this nested form. This nested form, when you think about it carefully, ultimately involves fewer computations than doing the standard form when you plug a number in. And they're just real basic computations, just add, subtract, add, multiply, add, multiply, add, multiply. Where adding could be really subtracting because you're adding a negative number. Okay, and this nested form is not going to go away. We'll see it as we work into chapter 3. We'll be thinking about nested forms sometimes. So you want to get used to that. We can apply this also to Newton's method. Say we apply Newton's method to this polynomial again. We know the roots, what they are, but just for the sake of simplicity, let's pretend we don't know the roots. The one at 4/3 would be, when you look at the graph, unclear as to whether it's a rational number or not. If you plot this function from negative 3 to 3, say, there is a root at exactly 4/3 right there. That is the point 4/3 exactly, but you wouldn't know that just looking at this picture. We only knew it because we knew the factored form ahead of time. So you might look at this and say, that could be, for all I know, an irrational root. So let me apply Newton's method to it. Maybe with 1 as an initial guess. In other words, we need to use the formula for Newton's method. P sub n equals P sub n minus 1 plus, minus the ratio of the function, but divided by its derivative at P sub n minus 1. Capital P sub evaluated at P sub n minus 1 over capital P prime evaluated at little p sub n minus 1. We've got to evaluate a function value. Horner's method can do that for you more quickly than using the original formula. So if I pick P0 to be 1, I'm going to have to evaluate P of P0. I'm going to have to evaluate P of 1. Let's use Horner's method. Let's use synthetic division. There's my 1. Do the same thing, bring down the 3, multiply, add, multiply, add, multiply, add, multiply, and add. It looks like P of 1 is 6. Is it really? Actually, it's fairly easy to plug 1 in here, right? Because 1 to the 4th is 1, and 1 to any power is 1. 3 minus 1 minus 16 is negative 14. Plus 4 is negative 10. Plus 16 is positive 6. Yes, this is right. We're also going to need to find P prime of 1. P prime of 1 equals question mark. Turns out you don't actually have to find the derivative to find P prime of 1. Turns out you can use Horner's method once more synthetic division, on effectively the Q of X function, the quotient. It's not obvious why this works, but it does. Let me go ahead and do it, and I'll confirm it by actually finding the derivative and plugging in 1. So again, use Horner's method, bring this 3 down, multiply, add, multiply, add, multiply, add. Looks like it's negative 19. Double check, make sure there's no mistakes. It'll look good. I claim, so the 6 is P of 1. That's P of 1. P of 1 equals 6. I claim negative 19 is actually P prime of 1, though I'm not proving that at the moment. Let's confirm that it's right without a proof by actually calculating the derivative. P prime of X is 12x cubed minus 3x squared minus 32x plus 4. P prime of 1. I just differentiated this. And P prime of X. P prime of 1 then would be 12 minus 3 minus 32 plus 4. 9 minus 32 is negative 23 plus 4 is negative 19. It worked. Why does it work? I think I don't want to say why. Other than it's in the book, for sake of time, because we're starting to run low on time here. It's related to the division algorithm and also Horner's method actually as well. Let me just leave it at that for the moment. What this is now telling you is you can use Horner's method to apply Newton's method. P1 is going to be P01 minus P of 1 divided by P prime of 1. So for this example, that's 1 minus P of 1 is 6. P prime of 1 is negative 19. So we end up doing 1 plus 6/19. As a fraction, that would be 25/19. And as a decimal, that'd be about 1.3158. We know the true answer is 1.3 repeating, right? 4/3 is 1.3 repeating. We're fairly close. That would be P1. I could apply Horner's method again to P1. In fact, I will give you a homework problem where you're doing this. And you probably don't even need to use so many decimal places of accuracy. I mean, you could use the fraction if you wanted to, but that probably the fractions will not go away if you do so. It's probably good enough to say use just like 1.32 because, you know, Newton's method converges pretty rapidly anyway. So why bother with more decimal places here? Go back to the original polynomial and do the same kind of thing. We will need a calculator here to help. 1.32 times 3 is 3.96. add and get 2.96, multiply with positive 3.9072, add by subtracting 16. Okay, I didn't really leave myself enough space here. Multiply times, I'll just do it the rest in the calculator. Negative 15.9624. 96 would be what goes here. Add 4 to that would be the number that goes there. Multiply by 1.32. You get the number that goes there. Add 16. P of 1.32 is approximately 0.2095. I could then apply Horner's method to find P prime of 1 by continuing this. And whatever number I get right here would be P prime of 1. And then I could use Newton's method again. Since you already know how to do Newton's method with regular formulas without Horner's method, you can always check your answer. Okay, so that's an application of Horner's method. Thought we have more time for this. We've only got 4 minutes left to just mention some other historically important theorems. I'm not going to write them out. No, we can take a look at them in the book. Let's look at them in the book. Starts off this section with the fundamental theorem of algebra. Says if P of X is a polynomial of degree n greater than or equal to 1, so it's not a constant polynomial, with real or complex coefficients, which you could just say complex coefficients again, because real numbers are complex numbers. Then P of X equals 0 has at least one possibly complex root. And when they say possibly complex there, they mean non-real, is the way that the author is writing this. A better way to say that is a possibly non-real root. Again, because real numbers technically are complex numbers. This is actually a very hard theorem to prove. You need some pretty powerful tools, the most powerful of which is in complex analysis. And if you've got the tools from complex analysis, actually, once you've got those tools, the proof is fairly easy, but you got to build those tools up. And it's not clear that those tools will help you prove it. There is a purely algebraic proof of it as well. That's even harder. Complex analysis is actually the better way to go. At least one possibly complex root. But wait a minute, don't polynomials have more than one root if their degree is more than 1? Yes, they do. A relatively easy corollary to prove based on this is that they actually have n roots. An nth degree polynomial will have n roots, possibly non-real numbers, possibly repeated roots, as a corollary of the fundamental theorem of algebra. In fact, you could say this is still the fundamental theorem of algebra. If P is a polynomial of degree n greater than or equal to 1, again with real or complex coefficients, there exists unique constants, x1 through xk, which are the roots in this theorem here, that are possibly complex, meaning non-real numbers, and unique positive integers m1 through mk, which are typically all ones. But sometimes they can be bigger than 1. These are the multiplicities of the roots. So you can factor P of X in this way. An is still the leading coefficient, and then you have these linear factors raised to these m powers. Again, most typically, all the m's are 1s. Only for special cases that your roots are double roots or triple roots, and the m's could be bigger than 1. If you add up all the m's, in any case, you got to get n. So you're saying you got n roots if you count multiplicities. 1 minute here. Still, this theorem is important as well. Very important for us in sections to come. If P and Q are polynomials of degree at most n, so maybe they're smaller degree, and if P of X equals Q of X at k different values of X, where k is bigger than n, and by the way, these x's are not roots necessarily of p, then in fact the polynomials must be equal. If you've got polynomials of degree less than 10 that agree at 10 values, they must be equal polynomials. And finally, there's a theorem of Horner's method in the abstract as well as an abstract proof. It's not too hard to understand. It's a little confusing at first. It really is confirming what I showed you for the particular example, and it really is related to nesting, though that's not clear in looking at the proof. Also, the fact that p prime can be evaluated by synthetic division as a consequence of this line right here. Okay, we're out of time. That's it for today.